a new technology has barged into our society, and it goes by the name of blockchain. You've probably heard of crypto, NFTs, right? But blockchain is the technology that's behind those things. But here's the problem. Only 60% of consumers actually understand what blockchain is. But with so many present use cases of blockchain in our society today, it's important for us to understand what this is. I'll start with the first use case of blockchain, Bitcoin. Bitcoin is just a money system, something to replace banks, which is what we have right now. But why replace banks in the first place? Let me ask you another question. Why do you put your money in a bank account? Because you trust the bank to keep your personal details and your money safe, right? Why do you trust the bank? Well, you pay them in the first place, right? But what if that bank just decided to take all of your money and sell all of your personal details one day? The law would be on your side? Yeah, the law would protect you. But would it really? Canada actually closed or froze the bank accounts of citizens that were protesting, which goes to show that the law isn't actually always on our side because we put our money and our information in the hands of others, not ourselves. Now, what blockchain does is it helps us gain ownership of our own data and our own money. But I must warn you, blockchain is still very, very new. Lots of cryptos are still really new, so we can't necessarily say that they're going to solve economic inequality, but they're definitely taking a stab at it. It's still growing and it's still evolving. A really simple definition of what a blockchain is that it's just a list. It's a list of transaction records. For example, Sam sent Sarah 4 bitcoins. Also, there's no physical bitcoin, like there's a physical dollar bill. It's just records that say who sent who, how much. Now, a blockchain network is also decentralized and distributed. Distributed meaning that list that I was talking about, everyone in the network has a copy of that list. It's the same copy, but everyone has a copy. Now, a blockchain network is decentralized because for a transaction record to be considered a part of that ledger or list that everyone has, it needs to be validated by the entire network. So that means the entire network has to agree that this certain transaction is valid and can be accepted. That's what makes it decentralized. In a bank, it's just one team or one authority that's making the big decisions. But in this case, all of you are making the decisions about your own money. That's just a really, really simple rundown of how blockchain works, but it's definitely a bit more complicated than this. In this video, I'm going to talk about a really simple Python blockchain simulation that I created, which helped me engrave the parts of blockchain that are most important.
Now, before I dive into my code, I do need to explain something. In my previous explanation of what a blockchain is, I talked about how it's a list of transaction records. But to be more specific, transactions are actually grouped. A bunch of transactions that happened near or at the same time are grouped into something called blocks. And the list that I was talking about before is just a list of these grouped transactions, which are blocks. Now I'll show you my code. So if you can see here, the first thing I do is I create a class called chain, which we'll create an instance of later. Then I have a constructor down here where 2 lists are initialized. So first I have the blockchain list, which is a list of blocks. And then we have the pending list, which is a list of transactions that go in one block. In our add block function, which is later on in this code, this will make way more sense. Now, what I'm going to talk about here is the add transaction function. This basically just takes in the sender, the receiver, and the amount that the sender is sending the receiver as parameters, and it puts all this information into a dictionary. Then this dictionary is added to the pending class. This is basically how you add one transaction. Then if we want to call this function, you can see, if we go all the way down, we create an instance of the chain class. Then I have this for loop that basically creates blocks and then adds transactions to these blocks using the functions from the class. I want to specifically focus on this line. What this does is this adds transactions to each block. And you can see the parameters I give it are random. They're just random first names and last names and amounts, just to make the process less tedious. But if you wanted to, you could do something around this. You could do chain dot add transaction. And then you could clarify the name of your receiver or your sender and your receiver and how much you're sending.
A block is just a collection of transactions that happened near or at the same time, like I said before. To be specific, more than 500 transactions can go in one Bitcoin block. But a block also has some information. Along with the whole transaction information I was talking about, it also has the time at which these transactions happened, something called a nonce, a value that's used in that consensus protocol I was talking about, and a hash of the current block and the previous block. Blockchain is called blockchain for a reason. All of the blocks on the list I was talking about are connected. They're connected by each block having the hash of its previous block. If anyone tampers with one block on the blockchain, then the hash of that block will change. What happens then? Then the block in front of that block, its hash of the previous block won't match up with the previous block's hash. And then we can see, uh-oh, something's wrong. But how does this all work? For this, I need to explain what exactly hashes are. A hash is just a random string of letters and numbers. You can convert anything like a number, a sentence, whatever value into a hash. I'll explain how this works through a bread example. So you're baking bread. Let's imagine that you're baking bread. And obviously before you bake your bread, you put a lot of ingredients together and you have your dough mixture, right? I want you to think of the value that you want to convert to a hash as that dough. Then you put that dough into the oven and out comes your fully baked bread. I want you to think of that fully baked bread as your hash. Do you think that you can put the bread back in the oven and get your dough back? Probably not. You can't unbake a bread. The same thing's here. You can't convert a hash back to its original value. Another property of a hash is that, let's say you have the value my mom. You want to convert that sentence into a hash. If you go back and you add one S, like my mom's, and convert that into a hash, the my mom hash and the my mom's hash will look completely different from each other. Just that one change causes the hash to change entirely. So if we connect this to blockchain, if anyone, as I said, tampers with a block, that entire hash of the block changes and we immediately know something's wrong.
So now let me show you my code and how I computed a hash in my blockchain simulation code. So the first thing I do is I import two libraries for our code. The first library is the hash calculator. It's the actual thing that's able to convert a normal value into a hash, and it goes by SHA-256. And then we import a JSON library because it'll help us convert our block data into byte data, which is needed for us to use the SHA-256 algorithm or calculator in the first place. Let me scroll. We need to compute hashes in this code because we need the hash of the current block and the previous block in the first place. So what we do is we take our block data right here, this variable block, and we first convert it into byte form. Then, with this line of code, then we feed it through the SHA-256 algorithm and we get our hash and we return it for later use.
The last part of my program was adding and mining blocks. The people who do this are miners, and you've probably heard of them. Miners group transactions into blocks and they officially add blocks to the official blockchain that everyone has the same copy of. They do this by finding something called the proof of work. The proof of work is our consensus protocol. It's a way for everyone to agree whether a transaction is valid or not. And what makes a transaction valid or not is actually in its hash. What miners have to do is, let's actually go back into my bread example before I jump into that. Remember I talked about that dough. That dough is the value that you have before you convert it into a hash. If you change one small thing about that dough or that value, your ending hash is going to be completely different than what it was before. So in this case, what miners have to do is they have to add some kind of variation of characters so that the ending hash, the ending block hash, has a certain number of zeros in the front. They basically just have to run through random variations and add these random variations to the block's information to find out if it'll have a certain number of zeros in the front. And this random variation goes by the name of nonce. It was the nonce value that I was talking about before when explaining what goes in a block's information. It's computers that are actually running through these random guesses and variations to try to find that nonce, but these computers belong to miners. The entire process of mining is just really time consuming and expensive because it requires a lot of computing power to just guess random variations. But that is the role of the miner, and they are paid to do it. So if you decided to make a fraudulent transaction or make a transaction that wasn't true, you would have to go through the process of trying to validate your transaction by finding the proof of work, which is, as I said, time consuming and expensive. But realistically, there's one major flaw with proof of work or mining as a whole, and that is that it could potentially centralize a network. Here's why. The one with the most computing power can dominate a network because they can be the ones that are approving the most transactions and adding the most blocks to the blockchain because of how much computing power they have. That computing power allows them to run through random variations and find the nonce faster than other people. This means that we put one person in control of approving blocks to the blockchain, which just centralizes the blockchain. Someone really rich could easily just buy computing power and do that. This just goes to show how blockchain is still very much in the making, and there's still lots of flaws with it. There's definitely new consensus protocols coming out every single day, like proof of identity, proof of stake, etc.
So the last part of my program is adding and mining blocks. I'm going to show that on my Python, because I wrote this on Python, so this is my Python editor. First, I'll show my add block function. What this basically does, I'll do a very quick run through. It creates a dictionary called block with all the relevant information that we need about a block, like the timestamp, the transactions, the nonce. You can see that we set the nonce to a default 0 because we haven't found the nonce yet. We actually add 2 more things to our dictionary later on. So then we add this block dictionary to our blockchain list. Then we also clear the list of pending transactions because we've added the block full of the transactions for that block to the blockchain already. So for the next block that we're going to need or add to the blockchain, we need to clear the list of transactions for that because we don't want transactions from the previous block to go in the new block. Then we have this mine block function. We call this function here, and these 2 values you can see here are return values from the mine block function that we get. It's the proof of work, which is added to the dictionary, and the nonce value, which is updated to the block dictionary. So what exactly does the mine block function do? First, let's define what difficulty is. We set a value called difficulty at the top, which is equal to 4. I set it equal to 4. What the difficulty value is the number of zeros that you're going to have, that you want to have in the front of your proof of work for it to be considered valid or considered proof of work. You can make this difficulty value higher than what I made it, but I made it tiny as like a 4 because it takes a lot of time to find that difficulty if it's a large number, like 10. So what I do is I create a string of 4 zeros. And the reason why I do this is in the next line, I create this while loop that what it does is it compares the first 4 characters of the current block hash to that 0 list. And this while loop will just keep running until that first 4 characters is equal to those first 4, or to that 0 list of zeros, of 4 zeros to be exact. Now what happens in this while loop is we constantly change a value about the block, which is the nonce. For us to be able to change the hash in the first place, we need to change something about the block or add something to the block, right? That's why we're changing the nonce here. All I do is I just add 1 to the nonce until this while loop is true and until we have that difficulty value equal to that 0 list. So now let's go down here. Then once we've found that right proof of work and the nonce, we print it. We print the proof of work, and then we return the proof of work and the nonce, the updated nonce, which are both then added to the dictionary. Then if we go down here, this is where we actually print the blockchain. This is where we create the instance of class chain and then run class chain's functions to create an actual blockchain. I'm going to actually run this program to show what the end result is. First, I'm asked how many blocks do I want in the blockchain. Let's say I want to have 3 blocks. Then you can see, it's going to take some time. Block 1 is mined. You can see that there's 4 zeros in the front. Block 2 is mined here. Block 3 is mined. And then this is just our entire blockchain and information about each of the blocks that we validated. So this is just the number of the block, what the block's value is, or which block it is in the blockchain. And then this is the timestamp of when it happened. These are the transactions that happened within the block. You can see like the sender, receiver, the amount. Then we have our previous hash, which, because this is the first block, the previous hash is just going to be Genesis because there's no previous block. Then we have the nonce value and our proof of work, or our current block hash. Then you can see the same information repeat for each of these. Now, something you can notice is how the proof of work here, the current hash of this block, is equal to the previous hash of block 2. And that's supposed to be on purpose. These 2 hashes should be the same.
So that concludes the end of my video. The purpose was to just teach you basic blockchain concepts and how they work through my code. The focus was the concept, not the code though. So if you want to learn more about how every single line in my code works, I suggest that you check out my article. I linked it in the description. But other than that, I hope that you continue your journey in blockchain and found this video to be helpful. Bye bye!